So this talk is aimed at mathematicians and more formal statisticians, and it worried me when I was thinking about coming down here a few days ago what kind of talk to give, but then Tom Griffith sent me an email saying I'm going to be there too giving a talk, and the ideal talk would be there's a mathematical talk on this kind of material, and there's a follow-up of what the connections to behavior, and Tom's going to give exactly that talk tomorrow. So it's a very good team tag, and I can focus more on this mathematical side. Okay, so part of my goal is going to be to explain all those words in the title. It sounds like a very technical title, and I'm going to aim to convince you it's not so technical after all. So let me start with a little bit of sort of almost philosophical comments about computer science and statistics. So just like behavioral science and mathematical sciences, they were much closer years ago. So in the 40s and 50s, they were very, very close. People like von Neumann and Kolmogorov and others were really in both fields. And then they started to separate. But the most recent trends is that some of the easier problems in the fields have been solved, and to the harder problems involve the other fields, so they start to merge again. So from a very high level point of view, what computer science and computation, broadly speaking, have done well is to talk about data structures and algorithms for manipulating data structures. So if you first start to learn about computer science, it's kind of cool to see that they're not just arrays of numbers. You have things like linked lists and trees and those kind of things. So that's really, really neat. And computer science has done wonderful things with those kind of ideas, making very flexible ways of manipulating data. And it has something to say about cognitive science. In fact, ideas like SOAR and so on, that was really about those kind of data structures. That's kind of what drove a lot of the interest in that. There's other areas in computer science, like cryptography and so on, but that's one of the main contributions. What statistics has done well is managing uncertainty using probabilistic tools and justification of algorithms, sort of particularly justification, not just making algorithms, but how do you justify that you come up with knowledge from those algorithms. And each field has sort of not done the other half of it well. Statistics has not done a great job with data structures, and computer science has not done a good job with uncertainty. They kind of excluded, the bits were always ones and zeros, period. And so machine learning is not really a new field. So we're using the word machine learning a lot. It really is just a set of topics in statistics. It's not a new field. Classification, clustering, reinforcement learning, and so on. These are just decision theoretic statistical ideas. And when you try to link them to each other, you end up kind of talking about statistical theory. But what it's done sociologically is it helped to hasten this merger along. So it addresses statistical problems using computational ideas, and so both computer science and statisticians look at it and say, "Oh, that belongs partly to us," and they learn about the other field a bit. Now, this would be all kind of easy to write a history about if it weren't for this one issue, which is that statistical inference has two flavors, frequentist and Bayesian. So you can combine it with computation in kind of two ways. And this is not going to go away. So most of us in statistics are both a little bit frequentist and Bayesian. And we use the tools, I like to use the analogy of wave-particle duality. They're both correct in some way, right? But they kind of conflict as well. So you kind of have to get used to that if you work in the field. You can't just sort of pick one or the other. You really got to pick both, but you got to kind of learn where they conflict and where they help each other. So this talk's going to be mainly Bayesian, but there'll be a little bit of frequentist here and there. I should say that in the previous talk there was some Bayesian material. The update rules that you saw at some point, we started talking about state models, were Bayesian, but the analysis of them, that they converged, that was a frequentist analysis. And so that's a very common sort of thing to see in statistics. It's kind of a Bayesian algorithm and then frequentist analysis of that algorithm to show that it does something appropriate, like it converges or it has a nice limit law of some kind. Okay, so let me jump into then Bayesian, and let me talk about nonparametric Bayesian. So Bayes' theorem, you've all seen that, is the core of Bayesian inference. It's inverse probability. So the likelihood is usually something about the probability of data given the state of nature. You would really like the probability of the state of nature given data, that's the posterior, and to get from here to there, you have to multiply by a prior. So the usual way you write that formula is that you have theta be a Euclidean parameter. By that I mean it's a finite dimensional object. As you get more and more data, it doesn't grow in dimensionality. It's a finite dimensional vector. That's what we mean by this. And so the prior would look like that. There's now the likelihood, the probability of the observable given the state of nature. And then what you want is probably the state of nature given the data. All right. So that's parametric models. So non-parametric models, now there's a big literature in this that's really emerging. There's probably 100 people worldwide who work on this as kind of a full-time discipline. There's a conference on it. In that literature, it's the same, looks like the same formula, except theta is no longer finite dimensional. It is a general infinite dimensional object. You have an infinite collection of random quantities. Okay, now that shouldn't be that frightening. That's just what a stochastic process is. That's a definition of a stochastic process. Infinite collection of random quantities. Now, if we want to work with that, we have to have some good reasons to work with that, and we have to be able to show that statistically it's sensible to work with that, and computationally, with infinite things, we might run into some troubles. We're going to show that it's really natural in the computational sense because these objects now can be very flexible. They're not limited to a finite dimensionality. So it's not like an array where you had to say the dimensions are array. It's like an array that can grow. Or it's not like a tree that has a fixed depth. It's like a tree that can grow. And so kind of if you're a cognitive scientist, that may seem more kind of congenial to you because sort of knowledge shouldn't be stopped at some point. It should be allowed to grow. So G is now going to be an object like a tree of infinite depth or an array of infinite dimensionality. And then P of G is probability distributions of those objects. So those are stochastic processes. So a tree of infinite depth, there's an infinite collection of variables you need to describe that. And so that is a stochastic process. That's what this object is. Conditional on a tree or an array of some size, then you can talk about the probability observable. So nothing really new is needed there. All right? Now if that's a stochastic process, then this object here must be also a stochastic process. So now the whole point of nonparametric Bayesian, you now know what that title means, is the update from a prior stochastic process to a posterior stochastic process. But in some sense, it's not really that new. So here's some examples of stochastic processes that would be of interest. You can now open up a modern book on stochastic processes, not just Markov chains and kind of classical ones, but a lot of new ones, and talk about distributions on trees, or on partitions, or on infinite-dimensional matrices, or on copula, or on distributions themselves. So that's an infinite-dimensional object, a distribution. I can put a distribution on a distribution. Perfectly fine thing to do. It's done all the time. And a real Bayesian statistician wants to do that because they don't want to ever say, I believe the prior is that Gaussian with a zero mean and a certain variance. They want to have a distribution on distributions. I believe it's one of these Gaussians. Okay, very natural to do. One general tool that we'll use a lot here is something called a completely random process. And I'll tell you what that is later. All right, the other theme in the talk is hierarchy, and this also came up in the previous talk a bit. And it really is one of the links between computation and statistics. So in the statistical lingo, a hierarchy is just really a kind of form of recursion. That you have a random variable that itself has a distribution with parameters. Those parameters are themselves random variables. They have distributions with additional parameters, and so on. It's a recursive modeling structure. Okay? So in the parametric setting, this is widely done. In fact, most Bayesian models are hierarchical. It's very rare to see a non-hierarchical one. So it just means that parameters can have distributions that are themselves parameterized. And similarly, in the non-parametrics, we use stochastic processes. All right, so we're going to use hierarchical modeling to build kind of graphical style recursive objects using stochastic processes as our basic properties of quantities. All right, so a little bit of kind of theoretical, what is a parameter? So, this is more like, how do you start making a model in the first place? So, statisticians are not very good about sort of telling outsiders how they start to make models. They say, well, here's some parameters, here's a model, and that's what your starting point. But that's not really how it works. So rather, we kind of have qualitative notions that we come into a problem. We start thinking about them and then go towards a model. So one example of this is something called exchangeability, very famous theorem due to Di Finetti. So exchangeability is just the mathematical definition is that if I have an infinite collection of random variables and I permute them, I get the same probability distribution. So very simple definition. Okay. Di Finetti proved that if you have exchangeability, if and only if, then there's a representation of the joint distribution of any finite subset of those variables in terms of an integral over some stochastic process. Conditioning on the stochastic process, you have IID behavior of your random variables. It's a very simple formula, right? In one direction, it's trivial. If you have this formula, then these are clearly exchangeable because this is invariant permutation. So it's totally symmetric. So in that direction, it's trivial. It's this direction, which is non-trivial. It says if you have this exchangeability, if you scramble things up, you don't change distribution. There must exist a G and a distribution on G, such that when you integrate that out, you get back to this. All right, so the intuition here is kind of nice, which is an example of an exchangeable model is the so-called bag of words models for documents. So what Google does and everybody else who processes large numbers of documents. they assume that the words could be scrambled in the document. That wouldn't change something significant, the meaning in some sense of the document. Of course, it's a wildly stupid assumption, but it leads to fast algorithms, and Google does smart things with these things. And it's not so stupid as you might think at first thought. People often think that means IID, that the words are all independent, identically distributed in a document. And that's totally wrong. Exchangeability is a much deeper concept. So if I have an exchangeable representative document, if the first word in the document is pense, P-E-N-S-E, it's a French word, right? Now I have to make a bet on the second word in the document. I'd learned something. It's probably another French word. All right? And if I start seeing a bunch of French words, maybe I'll start learning it's about French politics. Maybe after a while it's about French politics in the 1960s. And then maybe after a while, blah, 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 right? You can continue to elaborate this notion, and after you've seen hundreds of thousands of words, you might really pin down very much what that document is about, make perfectly good, as good a predictions could ever possibly be made about the next word. So you've learned a huge amount about the structure of the document. All that's going into G. What you are doing is that you are learning about the specific realization of G that led to that document. Now there's some other document. The first word is probabilità. That's an Italian word. Okay, maybe the next word's going to be an Italian word, and maybe after a while I learn about this is a book, Italian article about probability theory. Maybe it's about martingales. Blah, 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 blah. I can start to learn all that. So G must be very rich to permit myself to learn about all kinds of documents. If it were a finite dimensional vector, no way. All right? And so in fact, for this theorem to be true, G has got to be itself a distribution on distributions. Well, P of G has got to be that. That's the generality of the theory. So that leads you as a mathematician to be interested in nonparametric Bayesian methods. It's the soul of the field of nonparametric basis, this kind of theorems. This is one such a theorem, and there's many others.
Distribution on the parameter of the family?
No, we're not going to. So this is kind of a deeper philosophical point. We didn't start with parameters of a family. We just said there must exist a second process. You can parameterize it however you want. This is more of a parameter-free kind of way of thinking. So this is exchangeability. There's also partial exchangeability. There's also all kinds of algebraic exchangeability. This is really part of a deep algebraic theory, and it links probability and algebra. If you have an infinite number of parameters, that's a very good thing. So when we say non-parametric, by the way, that doesn't mean no parameters. That means infinite number of parameters. It's kind of a bad terminology in a sense, but that's the terminology. So it's a good thing, and it means you don't have artificial limits on things that you can learn. And again, going back to kind of the cognitive point of view, that's what you would kind of hope, right? I mean, the brain's in finite size. It's not the right thing to analyze it is in terms of an infinite, unbounded notions. How do we compute with infinite numbers of parameters? All right, so one way to go about thinking about these hard computational and inferential issues is to think about, lots of statistics is just list of numbers, arrays, and that's not very rich. It's propositional. So, if you ask a computer scientist what's needed, they say, go up the Chomsky hierarchy. So we don't need just proposition. We've got to get some logic in there. So there's a huge number of papers and people writing about how do you bring logic together with probability. And I think that's fine. It's a great thing to be working on, but to me, that's not the powerful way to go. That leads to intractability just immediately. Right? And very little real success has come out of that discipline. So eventually, something will happen. But to me, there's other structures in mathematics that are very powerful and underexploited, in particular in combinatorics. So combinatorics is just magical sometimes. Just you do a little combinatorial manipulation, something that was really looking very complicated, suddenly looked easy. There's all these symmetries and all these And so anyway, there's a relationship between probability and combinatorics, and that's going to drive a lot of what we're talking about here today. All right, so here's a little piece of kind of combinatorics. It's kind of a little bit hidden here, but I'm going to jump right to some examples of how do you build up distributional distributions. Okay, just so I can give you some examples throughout the talk. So this is not a probability and stat audience, so you need to know what a beta distribution is. Here's 0, 1, and beta distributions have densities. They are distributions on the interval from 0 to 1. So the densities for this talk kind of tend to look like this. They have a parameter, so beta, I'm going to be talking about beta 1 comma alpha. As alpha gets large, these things tilt up more and more to the left. So that's the beta distribution. Okay, so here's a way to get a distribution on the integers. Okay, integers, there's an infinite number of them, so that's a good starting place. If we can put distribution on the integers, maybe we can then put distribution on other kind of infinite objects. Okay, so draw an infinite sequence of beta random variables 1 comma alpha naught. So beta k are just draws from it. So they typically are lots of small little numbers and a few big ones. All right, and now define pi as a different infinite random sequence in the following way. Pi 1 is beta 1, and then the next pi value is gotten by breaking a stick. So here's a stick from 0 to 1. You break off a fraction beta 1 of it, and that's your first pi value. Then the remainder of the stick is 1 minus beta 1. It goes from here to here. And you break off a fraction beta 2 of that, and you call that pi 2. And then here's pi 3 and pi 4 and so on. So you get the idea. It's really easy. And you can see easily, and you can prove easily too, that these pi values will sum to 1 with probability 1. And they're clearly random. So I now got a distribution on the integers. It sums to 1, and it's random, right? And it's an infinite collection, but it only had one parameter, alpha naught. So somehow it's kind of something simple here going on. And it turns out that, in fact, if you look at these realizations, there's lots of combinatorial structure that you can read off various marginal and conditional probabilities from this. Okay, so there's a whole theory of this. Right, but moreover, there's something even more interesting you can do with these things, which is you can, given that you have these pi values, you can now construct other kind of random distributions. So the pi's are now just to be used as weights, and these are atoms. So delta means an atom at some probability space. Now this is going to be an arbitrary space. Phi k is the location of the atom, and I'm going to take an infinite collection of phi k's from some distribution g naught on some space. This could be an arbitrary space. It doesn't have to be a real line. It doesn't have to even be a finite dimensional space. It could be a measure space itself, or it could be any Banach space, or whatever you like. So atoms on that space. That's what these things right here are. At locations, and then delta means an atom. And I'm adding up an infinite collection of atoms. These pi's sum to 1, so this is now summing to 1 over my space. It's itself a random, it's a distribution. Okay? So now you can see that you can use this tool to get all kinds of distributions on all kinds of spaces. And they have combinatorially nice properties because those pi values are generated in this nice compact way. All right. In particular, this object has a name. This is known as a Dirichlet process. G, this object right here, it's a random measure. It's random in two ways. The phi locations are random and the pi's are random. And it is clearly a measure. If you think about any little part of the space, a certain number of atoms fall in there and they have a certain total mass. So you give a mass to that region. And it's random because of this randomness. So you have a random measure. It's called the Dirichlet process. Okay, so that may be your first random measure, and this was studied in the late 60s, and there's been huge numbers of these things studied since then. All right, now you can use De Finetti's theorem and think about using this G in De Finetti's theorem. Okay, you might ask, what collections of X's lead to G being the De Finetti measure? All right. That's an interesting mathematical question to answer, and it has a nice answer. It's called the Chinese restaurant process. So this is even a simpler idea. This is one of these urn-type models. So it's very closely related to the pull your urn, which came up in the previous talk. So this is just this is a distribution on partitions. This is a special kind of distribution on partitions. And partitions, if I have n objects, I got large numbers of permutations, something called the Bell number. And as n gets large, I get larger and larger. Right? So it's clearly needs to be non-parametric. I can't characterize those with a finite number of numbers. First person sits at the first table with probability 1. That's customer 1. And then customer 2 joins that person with some probability, maybe a half, but in general it's some parameter. It's alpha naught. It's related with alpha naught. And the general rule is that you sit at a table proportional to the number of people already at the table. It's kind of a pull your urn style dynamics. After n people have come in, we have a random partition. Who sits with who? Right? You can prove lots of things about this because of some combinatorics. It turns out that on average you have log n occupied tables. Right? Moreover, it turns out that even though we did this in some ordering, that this is exchangeable distribution on partitions. That means the probability that I sit with him is independent of where we were in the ordering. If you scrambled us and made a new line, we came in the restaurant, the probability we were together would still be the same. Yes.
So the number of people on the table is countable?
No, it grows without bound.
Countable.
Yeah. Oh, it's countable. It's integers.
It's countable.
It's countable.
Yeah, sure.
Of course. So they're just people. There's no. Can't break people into pieces and put them around the table. Maybe that's another metaphor, but that's not this metaphor. Yeah. Okay. So that's now just a very simple stochastic process on partitions. And that is a model, a kind of a process that you can now build up into a fuller statistical model for clustering. In particular, if the first person who sits at a table, say this guy right here, draws a parameter vector for that table from some distribution on parameters, let's call it G naught, it's the same G naught as before, then everybody else in that table is going to inherit that parameter vector, and that parameter vector could be thought of as characterizing a cluster. So if we're talking about Gaussian likelihoods, this is all the prior, but if we're talking about the Gaussian likelihood, this would be a mean and covariance matrix. And so it would be a location and a shape in space. And then table 2 would have a different location and shape in space. And we have log n occupied tables, so we have log n clusters around our space. Right? And that's the prior distribution. So if I get more and more data points coming in, my prior is growing in size. And that's would be non-parametric, right? Nothing weird about that. All right? Now, having gotten some data generated from these distributions, that's what the customers are now. There's going to be like a data point associated with each of these little dots. We could then go backwards with Bayes' rule and infer the table structure, who's at which table, and how many occupied tables there are, just using Bayes' rule. That's the posterior distribution. So here's a little example of doing that. I generated data from this Chinese restaurant prior, and then I used a Gaussian likelihood, just like I said. So there's a mean and a covariance matrix got from some prior. That's the parameter for each table, and so each of these ellipsoids is one table, and then there's a bunch of dots coming from that ellipsoid. So now the goal then is for a statistician, that's just probability. For a statistician, it would be to erase these ellipsoids, just look at the blue dots and infer the ellipsoids. So that's what Bayes' theorem does for you. There's a distribution on all those objects. Yeah.
So the circles represent tables, and or they say
they correspond to tables.
Correspond to a particular table, and
one ellipsoid for each table.
Okay, and not all the ellipsoids exist at the same time.
There's in people you see more and more people are coming in here. There's fewer blue dots and more. After this number of blue dots have come in, I think it's about 20. There's a certain number of occupied tables, and it grows its log n. Right? And so here's all the occupied tables. There's that 5 ellipsoids, 6 ellipsoids. And each table's got a mean and covariance, so the ellipsoid is representing that.
And the dot represents a given population.
It's a customer around the table. So once I've got a table, and I got a mean and covariance for it, I put an ellipsoid down, and now maybe I have 4 customers there. They were all drawn from that distribution, that Gaussian. So they're going to be little dots in that ellipsoid, roughly. Okay. Yeah, so now how do you actually do posterior inference as a computational problem? And so this is not what this is a modeling talk, and so I don't want to get into this in a great detail, but it is actually simple to state. A whole Gibbs sampling algorithm is listed right here, which is a very simple dynamics, which is the following. That, so in Gibbs sampling, it's a general technique that applies to all kinds of stochastic systems. For this particular stochastic system, what you need to do is you take all the customers in a certain state, and you take one customer, you pull them out of the system, and you say, now where should that customer go sit conditional on all the other customers? So that's what Gibbs wants to do. And that would be a hard calculation to do if the combinatorial didn't come to your rescue. That would be a difficult conditional. But combinatorial comes to your rescue in the form of the exchangeability theorem, which is that even though that customer was in the middle of the list somewhere, by exchangeability you can move them to the end of the list and you haven't changed the distribution. So you move them in the list, and now all n-1 customers have already come in and sat down, and you're asking now where's the next customer sit down? And that's just the Chinese restaurant. They sit at a table proportional to the number of people already at the table. So it's very trivial then to figure out which table they should go to, and you keep doing this over and over again, and that's Gibbs sampling. So it's not state of the art. There are many, many other algorithms, but that's easy to explain on one slide. Okay. I think this remark is not so important, but for the more experts in the audience, this is closer to the pull you earn. I kind of pulled this slide out after I heard it mentioned in the previous slide. This is exactly the pull you earn. The probability of the parameter associated with the ith customer. So customers can share parameters. Everybody around the same table has the same parameter. So these have some duplicates. So the previous I-1 customer is coming in. What's the probability of a parameter for the ith customer? It's just you get a delta function at the previous parameters, because you might have set at one of the old tables. Or proportional to probability alpha, with probability proportional to alpha naught, you draw a new parameter. That means you sit at a new table from a distribution G naught. And so that is literally that conditional probability. And if you now take the product of all those conditionals to get the joint, you do a little piece of combinatorics. You take you take a product of these sums and you turn it into a sum of products, and behold, you look at a formula that's invariant to ordering. There's your proof of exchangeability. So that gives you a flavor. Sometimes this can actually be very easy. Yeah. Alpha naught in this case would be called a parameter. All right, we have also, all the thetas are parameters too, but they're growing in size. All right, alpha naught is just one parameter, but they're all parameters.
Will affect the
Alpha naught will affect the number of tables you get. And so as a Bayesian, you're probably going to want to put a prior on that and worry about how that controls the number of tables. So that's part of your statistical modeling. Good question. You'd often call that a hyperparameter and deal with it at the next stage of the analysis, but you have to deal with it, critically so. Okay, so now I'm going to turn to a little pictorial diagram of everything I've said. So to summarize everything I've said so far in one little pictorial diagram. And then after this talk, I don't have to do much math. This is a graphical model representation of Dirichlet processes that uses mixture models. Graphical models are usually used for parametric problems. In fact, 99.9% of all graphical models I've ever seen are all parametric. But you can use them just as well for non-parametrics. In particular, you can put a node in the graph, which is this G, which is an interdimensional distribution. Perfectly fine to do that. And so given G naught, which is this underlying base, we'll call that a base measure. It's the source of all the atoms. It has some distributional shape. And given alpha naught, which determines the stick breaking process, you can now get a realization G, which one realization might look like that. And then you repeatedly, that's the box, pick one of the atoms with probability proportional to its height, and you get a theta I. And then that's a parameter to some distribution, maybe a Gaussian, maybe it's a location parameter to a Gaussian, and you pick an xi from that distribution. Okay, that's what I did in generating that data with all the clumps. So I picked one particular theta naught, that was this ellipsoid, and then I got a data point from that, that's right there. And then I do this again. And now I maybe pick the same ellipsoid again, and I get another data point. Or maybe then I get a new ellipsoid, and I get a data there, and I keep going. And slowly I start to grow the number of ellipsoids and data points. And that's what I diagram kind of as a summary of that process. Okay. Now in the graphical model notation, it's very natural to ask questions about marginal probabilities. So if I were to take this diagram and I were to marginalize out that node, it's a stochastic process. I can integrate over like I integrate over a classical random variable. If I integrate out of it, it goes away. And now I just have that diagram over there, which has a distribution on the thetas conditional on these hyperparameters. You can ask, what distribution do I get on the thetas? Okay? And I've already told you, it's the pole you earn. So if you would start with this as a model, maybe as a psychologist, working on learning theory, you would have, maybe this is a natural model, it's kind of a little simple kind of chain model. You would observe that the result you're getting out is exchangeable on partitions. And you would say, oh, De Finetti's theorem, there must exist an underlying measure. When I integrate it out, I get here. And so you try to go back to this diagram. And you would have discovered the Dirichlet process by doing that. That's not how the history went, but the history could have easily gone that way. Here's an application of this, some work I did with Tom here in the room, and Dave Bly. So I'm going to talk a little bit of applications now. That was kind of some math, and now let's go to some of the what you can use these things for. So this is something we call the nested CRP, nested Chinese restaurant process. Okay, so here this is actually a hierarchy in which every node is itself a Chinese restaurant. Okay, so now we have this tool, we can start to use it in all kinds of mix and match in all kinds of structures. The depth of this thing is given itself by a stick breaking process. So it's an infinite tree given by breaking sticks. So we're putting all together all tools in a different way. All right, once you're at a given node, you have little tables inside of it, and at every table, a customer comes in, sits at that table, and that tells you which branch to take to go down the tree. So our metaphor is that of a sequence of evenings in a town, where the first night you eat in one restaurant, and the table you sit at tells you which restaurant you go to the next night. Then you go to that restaurant, and then you again pick a table, and then you go to another restaurant the next night, and you keep branching. So one person comes down, it's like a little ant going down a path. The next ant comes down, they'll probably go on the same path for a while, then branch off, and then another ant will come in, and you get these little paths of reinforcement down this tree. Okay, now we're going to turn that into a document model in the following way. Once you picked a path down the tree as an ant, we're going to now generate a document based on that by repeatedly picking a level from the tree according to stick breaking. And then once you've picked a node along that path, there's a little distribution on words associated with that level of the tree and that node. Okay, so maybe it's a little word that's associated with travel, and you'd get a whole bunch of travel words there. Okay, and hopefully now, because of the tree structure, the words that are the most useful in all of the documents will percolate up to the top of the tree, and those that are useful for specialized documents will percolate down. Right, and that's what happens when you do Bayesian analysis, do posterior inference on this kind of model with abstracts out of conferences and so on and so forth. So we did a bunch of these. Let me just sort of skip over that slide. Here to show you one result. This is from the journal, the ACM, a computer science journal. The words at the very top, the highest probability words were function words. They just percolated right up to the top because they're used in all documents. And the next level, you got words that look kind of like a computer science curriculum. You've got the complexity, the algorithms, the networks, the programming languages, and so on. So you've probably seen these kind of topic diagrams before. My group's done a lot of these over the years.
So how easy it is to generalize this onto diagram that we know makes more sense?
Yeah, let me just say there's work on that, there are papers on that, and it's not, diagrams are not hard to generalize this to. Yeah, you can build language models with this and do all sorts of things. This is kind of a topic-based language model, and there's now a big literature on these things. I find this one particularly nice and interesting because it's got this multi-resolution structure. You're high-level topics from lower-level topics, and I just like that. And it's just done with these Chinese restaurant ideas used in a slightly creative way. Here's, I guess a lot of your psychologists, there's psychology. The of also percolated up to the top, and then you got model, memory, self, social psychology, motion, vision, molecular, drug, food, brain. That doesn't look too bad as a psychology curriculum, and then you keep going down. This is an infinite tree in general. We've cut it off at 3 to show it. Here's a completely different application. To show you the same tools can be used in very many different ways. A part of the protein folding problem, I've been working with people at University of Washington on protein folding for a few years. And one of the subparts of there is to model the backbone of the protein. So a backbone is at every amino acid you have 2 angles, which are the dihedral angles of the chain as it moves along that part of the amino acid backbone. And if you plot those dihedral angles, they're called phi and psi, over all instances of, in this case, alanine, over a big protein data bank, you get these kind of plots, and these are called Ramachandran diagrams. So, this is kind of really quantum mechanics is underlying this. This is the alpha helix region. It's because things like the hydrogen bind, so you kind of get certain angles going around a helix. And there's beta sheets up here. It's again kind of just from, there's a chemistry behind this. There's all these kind of little clumps and everything that, there's not really an explanation for. Well, some of them there is, some of them there isn't. And, I look at this and I think Dirichlet process mixtures, right? It looks like there's some big clusters and some little tiny ones, and it looks like a Chinese restaurant. All right, but now there's a more interesting, so we fit Dirichlet process this, by the way, and it fits very well, and it is being considered now for use by the protein folding people as their backbone model. But there was even a more interesting problem here, which is that amino acid occurs in a chain, so it has a neighbor on the left and a neighbor on the right. And the side chains protruding off of that have different shapes, depending on, there's 20 amino acids, they all have different shapes. And then that'll, the chemical property, the shape of the size of that will then push the alanine, in this case, in different ways. And so if you were to condition on your neighbors, you would be able to make a better prediction than if you didn't condition. So we really have is not just one diagram, we have a whole linked set of clustering problems. We have 20 on the left and right, we have 400 separate diagrams that are being laid on top of each other there. And if we were to separate them out and analyze them separately, we might do better. But of course there are some aspects of those diagrams which are similar. And so we don't want to completely separate, we want to kind of partially separate them out. And so that brings in the idea of hierarchy, which I was raising earlier in the talk. How can we separate things out because they're somewhat different, but allow them to still be linked together so that we share things where we can share things? That's a key issue in statistical modeling. Here's another example this is a genetics problem where a very similar issue comes up. In genetics, you've all probably heard about SNPs. There are polymorphisms, of which there are millions of them available nowadays, known. And if you look at M binary markers, or SNPs, where M is at all large, of course you have 2 to the M possible patterns of those markers. That's called a haplotype. If you look along a single chromosome and you look at M polymorphisms, places where humans differ, you could have 2 to the M possible humans. But if you look at a real human population, you get nothing close to, even if M is at all, even modest, you get very much fewer. And the reason is because, a few thousands of years ago, there was maybe there was a bottleneck in the population. There were a few ancestors, and their chromosomes were what are being passed down to us, and then slowly broken up by recombination and mutation. Okay, so inferring these haplotypes is a really important genetics problem. The problem is the data that you get are called genotypes. They are unordered pairs of markers. So here's a haplotype. A, big A, little c. And here's another haplotype, little a, little b, little c. These are homologous chromosomes, okay? So what you get in the data is actually you blend these two. So you just learn that at this site, there's capital A and little a. You don't know which order, who's on which chromosome. And similarly, big B and little c. So this is consistent with lots of different underlying chromosomes. And that didn't help you because what you're trying to learn about is there's a big A, a big B, and a little c, then there's a bad X over here, which is a bad disease. Because the human who had that haplotype a long time ago had the mutation which led to that bad disease. So if I could infer that you have that haplotype, then I'd know that I should predict you have a problem. And if you had that haplotype, then you have no problem. So I got to go backwards from here to here. All right. So if you have a large number of these, then it turns out the problem is track is a mixture model problem. That's exactly because of Mendel's laws. Okay, and so you can now write down a mixture model, and the whole issue about it is that you don't know the number of clusters a priori, because that's the number of haplotypes in the population. I don't know that. That's one of my main parts of my problem is figuring that out. All right, and so that's where classical mixture models would not know what to do. They have to assume they know the number of clusters a priori. Chinese restaurant, you don't assume you know the number of clusters a priori. Okay, so it's a very natural application of these ideas. But now, even more interestingly, if you have multiple groups of genotype data, so ethnic groups, for example, I have a bunch of Asians, a bunch of Africans, a bunch of Europeans, and I have genotypes from all of them. Well, I might like to separate them out because they do have some different haplotypes. But on the other hand, we all came out of Africa originally, and we have a lot of the same haplotypes. Africans just have more haplotypes than everybody else, but we have a lot of African haplotypes. All right, so you would really like to do separate clustering problems, but still draw them together, and you need to do hierarchical modeling. In the interest of time, I think I'll skip this application, but just let it be said, we have a whole long paper on this now, where statistical parsing can be thought of. I guess if Chomsky knew, I guess I'd get into this more, but you need to learn the rules of the grammar, and the main progress has been made by assuming you don't know a priori what the rules are, but you treat it as a clustering problem. In particular, you don't have that sentence goes to noun phrase, verb phrase, right? Rather, you have what are called lexicalized grammars. So that a verb phrase is a different verb phrase if it has certain kind of head word underneath it than if it doesn't. Crucial that people went to these lexicalized grammars. But now you don't know a priori which symbols to use in your grammar. Noun phrase / some head word. Why should I have used that instead of some other? Right, so you treat it as a clustering problem. That's what people do in statistical NLP, and they've made a huge amount of progress. The world's best parsing systems that are really now usable are based on these ideas. Right, now the issue though is that the same rule can get used in many parts of a parse tree. Noun phrase can be used over here and over here. So again, it's a separate clustering problem in different parts of the tree, but you want to allow the same rules to be used in different parts of the tree. So it's a multiple clustering problem again. Maybe next to last example is a classical open problem in hidden Markov modeling has been to, so hidden Markov model is just a doubly stochastic Markov chain. You have stochastic states which are discrete, and you have observables that are conditionally independent given the states. So here's the Markov chain. Those are not observed, and the observations are hanging off of those. What if you don't know the number of states in this latent process? Big open problem for a long time. There's some ad hoc techniques on that, and there's some model selection techniques which don't really work. Well, this turns out to be very naturally handled within this formula as I've told you about. So the natural thing to think about is a stochastic matrix. So a row, remember in a Markov chain, a row is just a transition to all the next states. So the current states, for all the current states, I have a transition to all the next states. Right? So if I don't know how many states there are, it's natural for every row to be a Chinese restaurant. Where I come in, my transition to the next state is, everybody transitions to a few next states, and slowly there's more and more next states available as the chain starts to occupy more of the space. Well, if I did that independently for every row, I would get no overlap among these next states. Because the parameters chosen up here and these would have overlap with probability 0. So I'd get a kind of a branching out, bushy structure, I wouldn't get a chain. All right. But if you treat this as a hierarchical model which links all these rows, it turns out you can solve this nonparametric hidden Markov model problem. You can build HMMs that don't know the number of states a priori. Last example is image segmentation. Big open problem for a long time. Not so open. People have made a lot of progress on it, but still it's not satisfying. I want to take a camera, I want to get this visual scene, and I want to separate you out from you, and I want your face out from your shirt, and all the little pieces of pattern on your shirt, I want to separate them out and everything. So that really is a partitioning problem. And so I really need to get if I'm going to be Bayesian, I get a distribution on partitions, and I can't assume I know the number of partitions a priori, clearly. Okay. And moreover, then I don't want to partition locally separately here and here. I want to couple them, okay, clearly. So I have the same problem. So I hope I've convinced you, lots of applications demand these kind of flexible models. In this case, we're just working with clusterings and distributions on permutations and these kind of operators. Very simple combinatorics, but still widely useful. Okay. Can you tell me about my time? I haven't been paying enough attention.
So about another 8 minutes.
Another 8 minutes, okay. Okay, I think I'm going to skip to a slide which kind of shows you how to solve this hierarchy, bring this hierarchy together with Dirichlet processes. And I think what I'm going to do is just kind of skip a couple slides. You can kind of see the pictures and kind of see what we're going to work up to. So my colleagues and I have worked out something called a hierarchical Dirichlet process, which is kind of one of our core pieces of technology. It can be used to solve all the problems I've just talked about. And on this slide, I have kind of the whole story in one slide. Okay, so think about maybe for concreteness the genetics problem. So I've got Asians, Africans, and Europeans. And I'm trying to put a distribution on the haplotypes for each of those. So it's open-ended number of haplotypes. Okay? All right, so the way I'm going to do that is I'm going to have a distribution H, which is the bag of all possible genetic polymorphisms that humans could have. So the mother of all haplotypes. Okay? Then I'm going to randomly generate a specific set that the specific realized human population on Earth has actually realized. Right. Then from that set, I'm going to resample this as a Dirichlet process with this as the base measure. It's discrete instead of continuous. So I'm going to resample from these with different heights now because I'm breaking sticks again to get from here to here. And that's now the Asians, Europeans, and Africans. So they have the same locations of the clusters because this was the base measure passed into each of those as the G naught. You can't get new atoms. But their heights will all differ. So the Africans can concentrate over here, the Europeans over here, and the Asians over here. The heights are different. So they get to share the same atoms, but they emphasize them differently. Of course, there could be some non-overlaps too. Having gotten a haplotype, then the rest of this structure is just the genetics of Mendel's laws of how do you turn a haplotype into a set of chromosomes. Okay. All right, so that is a successful model for that problem, but all the other ones I've told you about. So we have built a parser based on this, which gives state-of-the-art results. We have an image segmentation scheme, which is the world's best current image segmentation scheme. And then the protein folding application, we've also done that as well. So let me just kind of put a concluding footnote on the mathematical side of this. Having described this model now, you can ask about various marginal probabilities like we did in the previous case. You can ask what happens if I marginalize out G naught, which is kind of the underlying source set of all the atoms, with the local atoms in all the populations. Then I would go down to this diagram here, which just induces the distribution of all the kind of realized haplotypes in individuals, indexed by both their population and each which individual they are. And you can ask what that is, and we've given that a name. We call that a Chinese restaurant franchise. And it works like this. You have not one restaurant, you have a restaurant for the Asians, the Europeans, and the Africans. People come into the restaurant and they sit like before, proportional to how many people are at a table. And when they sit at a table, they go and grab a dish from a buffet line. And in the buffet line, they put a check mark next to the dish if they pick that dish. And then anybody else who goes up to the buffet line looks at the number of check marks, and they pick a dish proportional to the number of check marks. Okay? So the first person who sits at a table gets to pick a dish for the whole table, and they go to the buffet line to do that. So information gets spread across the different restaurants by the buffet line. So that's not just a cute metaphor. That actually is mathematically what you get if you marginalize out those G naught and GIs from the hierarchical Dirichlet process. That's the marginal of that stochastic process. Okay, so we applied that to protein folding. Let me just not get into the results, but these are the data, and these are the marginal probability contours that this model delivers back. This is what we give off to the protein folding people as energies for protein folding, and this is a state-of-the-art system for doing this. This is a diagram of all amino acids, and this is their current model. This is log probability improvement over their current model for all the amino acids. You can see wildly large improvements over what they were currently doing. So I'm going to skip NLP. I'm just going to say that this applies to non-parametric hidden Markov models, and we have a whole sequence of papers if you're interested on that on the HMM, which is a particularly interesting subclass of problems. You can not just work with chains, which what the HMM does, but you can work with trees, where along each branch it's like an HMM, but you can now branch, right? right? And you can have an HMM along each branch, transducers or trees. So we've also developed image processing applications that are based on so-called nonparametric hidden Markov trees. I'm going to skip over some of the results there. And then this last application is probably our one main killer app at this point. It really does work a lot better than what's available in the literature. Let me just, we have a paper on this. Let me just say that briefly what we do here. It turns out that the Dirichlet process, if you plot it kind of according to a zip law type plot, it doesn't have a power line. It has a very kind of long tail for a while, and then it drops off too quickly. And in real image data, when we actually did this, we calculated the probability of usage of each of the segments and the size, and the histogram over sizes. They tend to follow a power law, not entirely surprising. There's another stick breaking process based on not 1 comma alpha, but having a two-parameter family. You break sticks a slightly different way. You get longer tails, and those turn out to be power law tails. And these fit empirically the image, real-life images. And so we have built a model which uses not Dirichlet process, but Pittman-Muir as the local mechanism for getting pixels in an image, and then we couple them with Gaussian processes. And you have an infinite collection of Gaussian processes now, one for every one of your sticks that you're breaking. And so Eric Sutterth and I have worked on this model, and this is kind of a picture that shows it, and let me just show you a little bit of results. This is the prior, and this is multiple replicates, different images. This is the prior that this thing induces on visual scenes. This looks pretty good. This looks like it has some multiple scales. There's kind of objects and smaller objects. This is the power you get out of a Markov random field. This has been the thing that's driven the field of computer vision for like 3 decades or 3 now. Gieman and Gieman originally proposed this. You know, Hopfield picked up on it and so on. It's been a big thing. It turns out that if you use the Gieman and Gieman parameters or a hidden Markov field, they kind of did it and ran it for a while. It kind of looked like this. Right? It's kind of speckly. It doesn't look too bad, kind of like real images. And people said, okay, that's pretty good. It turns out they only ran it for 200 iterations because they had really slow computers in those days. If you then ran it for 10,000 iterations, like we can do nowadays, it turned out it's a flat image. There was no structure at all. Okay? And Markov random fields have a very narrow regime where they start to give kind of interesting results. It's not a good model for images. So this looks a whole lot better. And if you actually use that prior and then put it together with the posterior inference, then you can actually parse real visual scenes. This is a terrible, my screen looks good, yours doesn't. These are real visual scenes. This is test set images, and this is our parse of these things. Okay? And these are the current best, this is something called spectral clustering. This is the current best result in the literature. And you can see it breaks the image up really quite badly in various places. Okay, so the last 2 minutes, let me mention some work of Roman Thibault, who I think was here. Is Roman still here? Yeah. So Roman was in my group. He's now down at Irvine. So if any of you are interested in pursuing some of these ideas, you have a local expert. So let me just, in a couple of minutes, and I'm also going to set up Tom tomorrow. I know we'll talk about this kind of stuff a bit. So I've talked almost exclusively about something called the Dirichlet process. And it was just kind of because it was concrete, I could kind of teach you a little bit about these ideas, and it's been widely used. But is the Dirichlet process the only game in town? You know, no, by no means. There's lots of other stochastic processes which have interesting properties. So the Dirichlet process is a clustering model. You can sit at one table, only one table. Lots of other modeling situations, you might want to be able to sit at multiple tables. All right? A particular example I like to give is that when I go to Amazon and they do collaborative filtering on me, you know, I speak Italian, I'm interested in punk rock music, and I live in Berkeley. All right? Well, they give me recommendations that are about punk rock, about Italian, and about Berkeley. All right? How many people are in that cluster? Probably, you know, me. All right? So the original Amazon system, I actually know who built it. It was a clustering model. So they would have tried to find the person I cluster with and say, what other books did that person buy? And suggest some. Well, there's no one else in that cluster. But they still do a good job for me. Right, so what they are doing is they're essentially, they don't do it mathematically in this way, but they have a model in which you can sit at multiple tables. I can sit the Italian table and the Berkeley table and the punk rock table. All right? So I want to do that mathematically. And the beta process is a stochastic process that allows you to sit at multiple tables, kind of the short version of the story. And so Roman has worked on that. It's an example of another even broader class of things called completely random processes. They have independent increments. What happens in this part of the space independent from whatever happens over here. And that's really crucial for computational algorithms to be tractable. So beta is an example of that. Dirichlet is almost an example of that. And here is, if you draw from a beta process, you can now sit at multiple tables. And if you now ask which tables that, here's 100 different people, which tables do they sit at? this person sat at this table, this table, this table, this person sat at this table, this table, this table. So you can see some tables get a lot of occupancy and others not, and this is just one realization of that particular stochastic process. Okay, so I'm going to skip over some more talk about the beta process and now just ask the interesting question about the Di-Finetti theorem. So I'm going to finish the talk on this point. So remember Di-Finetti's theorem back in the beginning of the talk? We integrated over some g. I've now told you a new g, not the Dirichlet process which led to the Chinese restaurant. Now the g is the beta process. Does that lead to some other kind of stochastic process when you integrate over it? And it does, and it's something called the Indian buffet process. And so Tom, together with Zubin Garamani, invented this thing called the Indian buffet process, not from the point of view of Di-Finetti's theorem, but just as an interesting distribution on infinite binary matrices. Very clever to come up with this without doing the integral. So, and then Romain has worked on this since, and we have a paper that shows that, in fact, the Indian buffet process is the Di-Finetti integral. And so Tom may describe this more, but the Indian buffet process is just the following. A person comes into the buffet line in an Indian restaurant, and they eat a certain number of dishes. The next person comes in and eats some of those same dishes, but chooses a few new dishes, and so on. This iterates. And you now get a distribution on binary matrices. Well, that turns out to be the distribution you get by integrating over this beta process. So nice connections to be made. Many other connections can be made if you go to hierarchies of these things and do these for other kinds of processes. So I think I'm now done. I've made a kind of real quick dash through lots and lots of ideas, and I know that no one here understood all of it, but I decided I'd give this talk anyway because I thought it might intrigue you, even if you didn't understand all of it. This is kind of where mathematics and stochastic processes and statistics is these days. Okay, so a lot of times I go to talks in other fields, behavioral scientists or economists or et cetera, and they say, statistics is very limited. It can only do this and this and this. And I always get kind of a little irritated because they haven't followed it. It's a very big field that does a whole lot of things, and it's kind of like this elephant. Everybody thinks they know the trunk, so that's all there is to statistics. And so one thing I encourage you to do is really learn some modern statistics and try to use it in your own ways in your field. I have a bunch of tutorials on this kind of stuff and other kinds of a lot of papers, but there's many other sources for these ideas, and I really hope these ideas will diffuse more readily. Yeah, I'm done. So.
So for Chinese restaurant process, the assumption there is that the probability of choosing one particular table is proportional to the number of people sitting on the table.
Correct.
What kind of insight, intuition you have on why this assumption is realistic in terms of topic clustering or word clustering? How do they need to link together?
Okay, so it's not, the way you do it is that you look at real documents and you look at their empirical probabilities, and you try to see, do goodness of fit under your model. Okay, so that's what we did in the vision application. We did a goodness of fit test on the Dirichlet process, the Chinese restaurant process, and it didn't fit. Okay, so we were led to the Pittman-Yor model, which is an enriching of the Chinese restaurant. Basically, you sit at a table proportional to the number of people already at the table, but there's a linear increase in the probability of starting a new table. It's kind of the itchy person who doesn't really like to sit with other people. Okay, so there's a 2-parameter family now, so you get just 2 parameters, not a lot, and the goodness of fit went up a huge amount. So we knew, like a classical person, that would be a better model to be looking at. Now that's just our. So anyway, you don't just say I believe in this thing.
Have you guys applied this to build the whole Gandesh compressive sensing and belief propagation?
So I work a lot on that topic too, and I have a lot of papers on that topic.
How does this fit?
Really what's beautiful about that set of ideas is it's just good old-fashioned frequentist theory. So you're using a very, very simple model, linear regression with an L1 penalty. And you're saying under some ensemble, I will actually recover the support, even though n is much, much lower than p. Okay. So that's just frequentist. This was a Bayesian talk. I could have given a separate talk on those kind of ideas. At the end, there was a possible connection. So the beta process leads to these sparse binary matrices, which could be viewed as a prior for a regression with a sparse set of features. And so there is work on that in the Bayesian literature called spike and slab models. And people will not
propagation.
Sorry?
Belief propagation.
That's just an inference algorithm. That's just nothing fancy. Belief propagation is just another inference algorithm. I told you about Gibbs sampling. If you don't like Gibbs sampling, do belief propagation. And this was, again, not a talk about inference algorithms. This was about modeling. That's just a variation. That's a variational inference algorithm, belief propagation.
For your in your MRFs, you're talking about in your vision application.
Yeah.
What kind, if I was to use that in my research, what would be the structure of the links which I would use?
Okay, so I would not use an MRF in a vision application. I just think they're totally broken. And there's been other people who've had papers on this. They're not a good prior for images. They're a good prior for crystal structures and magnets. They are the crystal structure magnets. They're a very bad prior for images. They don't have multi-resolution structure. They have a very narrow regime where you don't magnetize to zero, all zeros or all ones. And it's just it's a bad start. They're discrete too. Why should you start with a discrete underline, force your image into a discrete set of underlying states, and then try to recover some continuous nature of images? So anyway, people have worked on it for 30 years. People have worked on it for 30 years, and it does not solve the problem. There is not a working MRF system that does good stabilization. So, well, you may be the first one. I would never rule out. If a student came out and says, I'm doing it, I'd say, if you have a good reason, go for it. Right? But I would have not a priori told you to do that. I think and you might want to consider doing a really fast turn there. Yeah.
So on this, on the application on the haplotype inference,
Yeah.
so we kind of know that different haplotypes are kind of connected to coalescence.
Yeah.
Does that satisfy exchangeability?
No. Coalesce, well, so it's a long answer. So in the naive way I presented here, the coalescent breaks exchangeability. The coalescent trees, if you average over the coalescent process, you get an exchangeable process. A Chinese restaurant is a certain kind of marginal or mutations on the coalescence. But if you want to use coalescence for inference, we're not doing that at all here. There are other people who work on that. That's very important.
So in your image segmentation,
yeah.
How does the overall, when you summarize it, do you separate? Does the algorithm separate the image according to the features we are familiar with? For example, the edges or the textures. Is it doing from that perspective? What is the algorithm?
Yeah. So this is a Bayesian system, so it actually gives you a posterior distribution on everything in sight. If you want a posterior distribution on where the breaks and the regions are, it gives you that.
For example, if you apply this to facial recognition, what would pick up?
Yeah, so this is one paper that Eric and I've done. Eric is really working, he's a vision guy, so we're really extremely hard on this. And I think there's a lot of applications for motion, for face, but also a lot of medical image applications. Because medicals, you have tons of data and you don't have a lot of ground truth. This is an unsupervised system.
So for the facial case, is the algorithm trying to focus on the eyes, the nose, or because that's
so we haven't worked on face side. I wouldn't want to speculate. People have worked on it so much that I wouldn't want to jump in there. But we would be using this for facial classification. That problem's solved. Right. But for there are other applications, tracking.